Hello. This week, while I'm out, you're going to be working on Module 16. And Module 16 takes what we've learned about exponential functions and applies it to real-world situations. So we did 16.1 already, where we started to deal a little more with exponential functions. And now it should be Monday, and you're working on 16.2, which is modeling exponential growth and decay. And so this is where we really begin to apply exponential functions to real-world situations. So our goal for this lesson is to be able to use exponential functions to model the increase or decrease of quantities over time. So for instance, like nuclear materials, right, radioactive stuff, decays over time. It gets smaller at particular rates, and it gets smaller. The way that it gets smaller, the rate that it gets smaller, can be modeled by an exponential function. And we'll talk about some instances of that here in a little bit. So that's our goal for the lesson, is to be able to use exponential functions to model the increase or decrease of quantities over time. And I do have that over here. I know it's kind of hard to see on the video, but if you listen, I think that you'll be able to catch what I'm saying. Also remember, on YouTube you can zoom in to see what I'm writing on the board. So if at any point during the video you want to be able to see something I'm writing on the board better, you should be able to zoom in, okay? Now again, then also, a couple of things I want you to remember as we begin this lesson. One is that an exponential function is like a geometric sequence, but with a domain that is all real numbers. So when we first encountered exponential or geometric sequences, we were dealing with starting at 1, and then all of our inputs were like 1, 2, 3, 4, right? So they were integer inputs. And they were positions in the sequence, the position number, and then we had the term value, and that was our input was the position number, our output was the term value. But now we're dealing with exponential functions, and exponential functions have the same characteristics of a geometric sequence, in that going from one position to the next is changed by a multiplier. We multiply by something each time to move along the function. But now we're not only dealing with those discrete values of 1, 2, 3, 4 as inputs, but our inputs can be any real number. And again, we've been dealing with this for a few lessons. We've been graphing the curves that go on both sides of the y-axis. Those are exponential functions. The other thing is to remember, as we get into this lesson, is that functions or relations can be written in three ways: as a table, as a graph, or in function notation. As a table, as a graph, or in function notation. Those are the three ways that a relation can be displayed or written or represented. And it's important to remember that, because sometimes if we have something in function notation that we want to draw as a graph, we need to go through the intermediate step of making a table. Or maybe we start with a table, we need to know how to write it in function notation. So it's good to remember that a relation can be written in all three of those forms: function notation, table, or graph. Okay? So let's get underway. So far, as we've dealt with exponential functions, we've encountered them in this form that I'm going to write on the board. We've encountered them in the form y equals a times b to the x. Okay? So remember, what makes something an exponential function is that it has a variable in the exponent. Our input is in the exponent. That's what makes it an exponential function. And so usually we've been encountering it here where a is sort of like that's our y-intercept. So that's the value when x equals 0. B is what in a geometric sequence we would call the common ratio. That's what we multiply by each time. And then we have our x, which is our input. Okay? So this is how we've seen exponential functions so far. All right? But now what we're going to start to do is model the growth or decay of a quantity over time. So we have a different input. That input is t for time. Okay? And we're going to start to refer to a part of that situation when we're dealing with a real-world situation. How much that quantity increases or decreases per unit of time is going to be called its rate. Its rate of growth or its rate of change. So for instance, if if we were dealing with one of those nuclear materials that decreases, that would be exponential decay. And over each period of time, you would say maybe it decreases by 50%, and then 50% again, and then 50% again. So that 50% would be its rate of decay. So we're going to be using R again for rate, okay? And then we're going to keep A to be our beginning quantity. Okay? So I'm going to draw a table on the board for two types of exponential models. Okay? There are two types of exponential models. There is growth. Something grows over time. So we're multiplying by a number greater than 1, right? Or something decays over time. Growth or decay. Decay meaning it wastes away. So then our rate by which it's changing, that it's being multiplied by, would be between 0 and 1. So with the notation we've dealt with before, okay, so if you can remember what we've dealt with in previous lessons about what happens depending on the value of A and what happens depending on the value of B, this will help you understand growth and decay. So with the value of A, for a growth function, when a quantity is growing over time, A is greater than 0, okay? And B is greater than 1, okay? So again, because we have an A value, okay, that is greater than 0, we have a quantity of something. And then the rate at which it changes is a factor greater than 1, because if it was a fraction, if B was a fraction, something between 0 and 1, it would be getting smaller every time you multiply by B. But since B is greater than 1, every time I multiply by something greater than 1, the quantity gets bigger, okay? So we have A greater than 0 and B greater than 1 for a growth model, okay? Then for a decay model, we still have A greater than 0 because we're dealing with situations where we have a quantity of something. So it's not going to start negative. So our starting value, our y-intercept, is going to be greater than 0 because we have a quantity of something. Whether it be nuclear material or maybe it's like animals as they reproduce, something like that, okay? So we have a quantity of something that's greater than 0. But when we're talking about exponential decay, where something gets smaller, okay, then what we multiply by each time needs to make it go from one quantity to a lesser quantity. So that means that B is between 0 and 1. Okay? So B is between 0 and 1. B is a fraction or a decimal, right? Something less than 1, but it's still positive. So that means every time we multiply by B, the quantity gets smaller. So that's where, like, if we said our rate was 50%, a 50% decay, right? Then that means that it's shrinking by 50% each time. We're multiplying by 0.5 every time, okay? So for instance, but now we are going to deal with a different form. This is the form we have dealt with, okay? Y equals A times B to the X. For exponential models, when we're modeling the growth or decay of a quantity over time, we're going to deal with a different form, okay? So this is the exponential model form, okay? For a growth function, it is y equals 1 plus r to the t. And remember, I said that t is our input because we're trying to show how something changes as a function of time. So we would say, like, after 5 minutes, so you would type in 5 minutes. You would put in 5 minutes where the t is. Or if it's after, maybe we're judging in years, it'd be 10 years, you'd put in 10 for t, right? Something like that. Now, this r, again, is the rate by which the thing grows. So again, like if it's a tree that grows by 50% every year, right? So we say first it's at 10 feet tall, then in a year it's at 15 feet tall. This would be really fast growth, but stick with me. So a tree's at 10 feet, then after a year it's at 15 feet. It grew by 50%. 50% of 10 is 5, so that gets added onto the 10 to make 15. So that's why we have a 1 plus r. Because if the tree grows by 50%, we're not multiplying by 50% each year. We're multiplying by 1 plus 50%, 1.5 each year. Okay? Each year we multiply by 1.5. All right, and then, oh, sorry, and there's an a here. Because we have to have our starting quantity. Okay? so the starting quantity, times 1 plus the rate of change each year. Okay? Now, finally then for the decay, just a second. Okay, for the decay, we say y equals a times 1 minus r to the t. For similar reasons. So if you start with a quantity of something, but it shrinks by 50% or 25% every year, okay? So let's say we have a tree that is diseased, is 10 feet tall, each year it shrinks by 25%, okay? So we would start at 10. After that first year, how tall would the tree be? Well, it would be 10 feet minus 25% of that is 2.5 feet. So it would be 10 minus 2.5 is 7.5. So we would multiply by, in this case, if it's shrinking by 25%, we'd go 1 minus 0.25 is 0.75. So each year we'd multiply by 0.75. What's left at the end of that year is 3/4 of what we started with. Okay? So we'll unpack that here in a moment, but just to point out that our independent variable, our x, for an exponential model is t. Okay? So our independent variable is t time. Okay? That's when we graph, that will be our x value, our horizontal characteristic. Okay? And our dependent variable is the quantity of whatever we're dealing with. So the height of a tree, the number of bunnies, the mass of a nuclear material. Okay? So that unit will change each time. But understand that we're plugging in a time, okay, over which the growth or decay occurs, and we're getting out some unit of quantity, be it mass, or number, or volume, or height, or length, something like that. Some unit, some measure of quantity is what's coming out of the function. That's our y value, our vertical characteristic, when we graph the relationship. So, let's do an example. Okay? Okay. Okie doke. So, our example is on page 754. So if you want to turn in your book to page 754, we're looking at B. Okay? And I'm not going to look real closely at filling in the boxes, but if you can follow along, you'll be able to fill in the boxes with me. So it says this. It says, a baseball trading card is sold for $2, and its value increases by 8% each year after it is sold. Find the value of the baseball trading card in 10 years. So again, it says the card started at $2, and it increases by 8% each year. So is that growth or decay? Growth, right? Because if it increases, the quantity, the price is growing. Okay? So that means that we want to write an equation that is y equals a times 1 plus r to the t that models the way the price of this baseball card changes. Okay? So we know that we need to find a and r. A is our starting value, our starting quantity, in this case price, and r is our change per unit of time. Per unit of time. So we're dealing with a starting value of $2, so A is 2. And we're dealing with a rate of change, a growth rate of 8% per year. Okay? So our R is 0.08. And it's important to note that because this rate is 8 cents per per year, 8% per year that it goes up, that means our t is going to have to be in years. Another thing to note is that I wrote 0.08. The book says 8%. It's expected that you can transition back and forth between percentages and decimals, right? So that's a pre-algebra concept. So percentage to decimal. Okay, so I'm going to put these numbers into this form. We're going to say y equals 2 times 1 plus 0.08 to the t. Okay? So now what we're saying is, so now we can simplify what's inside the parentheses to say y equals 2 times 1.08 to the t. I just added 1 and 0.08. And that's because, so think about this, if the card started at $1, let's say, and in the first year it went up by 8%, well, 8% of $1 is 8 cents. So at the end of that year, it's going to be worth $1.08. See, so we're not just multiplying each year by 0.08, we're actually multiplying each year by 1.08 because we keep that initial quantity and add on the increase. Okay, so that's why 1.08 in here. All right, so now we want to find the value in 10 years. Okay, so that means that find value in 10 years means t equals 10. So now we're going to plug in 10 for t. Okay, so y equals 2 times 1.08 to the 10th. Okay? And at this point, you would use your trusty calculator and make sure you type it in correctly. I would go open parentheses, 1.08, close parentheses, to the, so the little exponential caret, 10 equals 2.15. 2.159, we'll say. Okay? So y equals 2 times, and 1.08 to the 10th is 2.159. Okay? So now we take that and multiply by 2, and we get 4.32. And it's approximately 4.32. So the value after 10 years is $4.32. Okay? $4.32. But you know what? What if I wanted to know what the values were, not just at 10 years, but I wanted to kind of see the progression? Well, I could do that as a table, right? So I could say, this is my table of values for the card. I have t, which is time in years. And I have my y value, which is dollars that it's worth. Right? Dollars that it's worth. So let's make a table. Well, at 0 years, at the beginning, at time 0, y is 2. Right? So if I plug in 0 here, anything to the 0 power is 1, times 2 is 2. Okay? So that means that when the project started, when I first bought the card, when no time had passed, the value was $2. All right? But then let's say after 3 years, so if I plug in 3 for t, 1.08 to the third times 2 should tell me the price, and that price is $2.52. Okay? So in 3 years, it went up 52 cents. Then 6, after 6 years, it becomes 3.17. And again, you can find all of this by taking the time t and plugging it into this expression, and it spits out the price after that number of years. After 9 years, it gets to $4. Okay. Then after 12 years, it gets to $5.04. See, so now that I have data like this, I could ask you, so how long does it take for the value of the card to double? So if I said a card started at $2, it goes up by 8% per year, how long would it take the value of the card to double? Right? Well, it started at 2. Doubling from 2 would be 4. We go down our table of values, we notice, the first time I hit 4 is at 9 years. It takes 9 years for the value of the card to double. Right? So once we can track data like this, we can start to answer questions about how the data behaves over a long period of time. And it can allow us to predict maybe how we make decisions for here, like, are baseball cards a good investment, right? If you can predict an 8% gain a year, they'd actually be a pretty strong investment, but they're not really that solid. Okay, so just notice, like, lastly, the y-intercept when x equals 0, the y-intercept is the starting value. And now that you have this table of values, you have ordered pairs that would help you to graph the function. So now you're going to be doing, on page 760 to 761, numbers 7 through 16. Once you've finished all of those exercises, you can have access to the teacher's edition of the book and check your answers. If you get any wrong or you're struggling with any, go back and try to fix them, okay? When I return next Monday, all of these will be due. You'll turn them in. And we'll answer any questions. And then on Wednesday, you're going to take the Module 16 quiz. All right? Happy mathing.